Hello everyone and welcome to this lecture on feature engineering in BigQuery. So this lecture is specifically to BigQuery ML component of BigQuery, and let's see what feature engineering features are available in BigQuery. So BigQuery feature pre-processing overview. Feature pre-processing, including feature creation and data cleaning, is a crucial step in developing a machine learning model. It is often referred to as feature engineering. So BigQuery ML facilitates feature pre-processing by offering two types. One is automatic pre-processing, which is carried out during training and and second is manual pre-processing, which can be done using the transform clause in the create model statement or by using pre-processing functions on the training data before creating the model. So feature pre-processing type, we have automatic pre-processing, and BigQuery ML performs automatic pre-processing during the training phase. And then we have manual pre-processing. Users can define custom pre-processing using manual pre-processing functions in the transform clause of the create model statement. These functions can also be used outside of the transform clause to process training data prior to model creation. Okay, use ml.featureinfo function in BigQuery. So ml.featureinfo function allows users to retrieve statistics of all input feature columns, assisting in understanding the properties of the data being used. So this is something specific. After you create the model, you can use ml.featureinfo, and that will give you all the statistics of your input feature columns, and that will help you better understand the properties of all the data that is there in the model and the model is trained on. So it looks something like this: is ml.featureinfo, and then you have model, and you have project id.dataset.model. So how would you use it in once you have your model in BigQuery? You can do start from ml.featureinfo model, and if you are in the same project, no need to give project id, just dataset and the model name, and this will return all the following columns: input, the name of the column in the input training data; min, the sample minimum, this column is null for non-numeric inputs; max, the sample maximum, this column is null for non-numeric inputs; mean, the average, this column is null for non-numeric inputs; standard deviation, this column is null for non-numeric inputs; category count, the number of categories, this column is null for non-categorical columns; null count, the number of nulls; and dimension, the dimension of array struct columns, and also this column is null for non-array struct columns. Then you have automatic feature processing in BigQuery ML. So BigQuery ML performs automatic pre-processing during training through the create model statement. This pre-processing comprises missing value imputations and feature transformations. So in statistics, missing data can be replaced with substituted values, a process called imputation. So within statistics, if there are any missing values, they will be replaced or substituted, and these are called substituted values, and the process is called imputation. And BigQuery ML treats null values as missing data during training and prediction. The handling of missing data varies based on the column's data type. So data type specific imputation methods in BigQuery ML. BigQuery ML uses varying imputation methods depending on the data type of a column. For numeric columns, null values are replaced with the column's mean value. For one-hot or multi-hot encoded columns, null values are mapped to an additional category. For timestamp columns, a mixture of method is used, and for struct columns, each field is imputed according to its type. So we'll just see in detail like data type specific imputation method in BigQuery ML. So we have numeric. So in both training and prediction, null values in numeric columns are replaced with mean value of the given column as calculated by the feature column in the original input data. And we have one-hot and multi-hot encoded. In both training and prediction, null values in the encoded columns are mapped to an additional category that is added to the data. Previously unseen data is assigned a weight of 0 during prediction. And we have timestamp. timestamp column uses a mixture of imputation methods from both standardized and one-hot encoded columns. For the generated Unix time column, BigQuery ML replaces values with the mean Unix time across the original columns. And for other generated values, BigQuery ML assigns them to the respective null category for each extracted features. And we have struct. In both training and prediction, each field of the struct is imputed according to its type. Okay, now feature transformations in BigQuery ML. BigQuery ML has default transformation for different data types, including int64, bool for boolean, array, timestamp, and struct. These transformations are part of the pre-processing phase during model training. Transformation methods are specific to each data type. For numerical columns, standardization is the default method. For non-numerical non-array columns, except timestamp, one-hot encoding is employed, and arrays undergo multi-hot encoding. Timestamp columns have a specific timestamp transformation, and struct columns are expanded into separate columns. So these are the transformations. So we have int64 numeric, big numeric, and float. So standardization. So transformation method is standardization. For most models, BigQuery ML standardizes and centers numerical columns at 0 before passing it into training. The exceptions are boosted tree and random forest models, for which no standardization occurs, and k-means models where the standardized features option controls whether numerical features are standardized. And we have bool, string, bytes, date, time, and time. We use one-hot encoding transformation method. So for all non-numerical non-array columns other than timestamp, BigQuery ML performs a one-hot encoding transformations. For all models other than boosted tree and random forest models, this transformation generates a separate feature for each unique value in the column, and label encoding transformation is applied to train boosted tree and random forest models to convert each unique value into a numerical value. Then we have array, for which we use multi-hot encoded, and you can read through it. Then we have timestamp. Then we have timestamp transformation. For timestamp, when a linear or logistic regression model encounters a timestamp column, it extracts a set of components from the timestamp and performs a mix of standardization and one-hot encoded on the extracted components. And for the Unix time in seconds component, BigQuery ML uses standardization, and for all other components, it uses one-hot encoding. Same we have struct. We'll use the struct expansion, and array of structs, no transformation. Okay, timestamp feature transformation in BigQuery ML. So BigQuery ML extracts time-specific components from timestamp columns during pre-processing phase. These components include Unix time in seconds. So this is important because for timestamp, there are a couple of use cases like you can extract time in seconds. Like for example, you can have day of month, day of week, month of the year, hour of day, minute of hour, week of day, and year. Because a lot of use cases employ something like whether it's weekday, weekend, which time of the day, whether it's before afternoon, after afternoon, depending on seasons and months. So all these factors are there. That's why timestamp feature transformation has some extra specific components. And for each extracted component, a specific transformation method is applied. Okay, for example, Unix time in seconds undergoes standardization. All other components such as day of month, day of week, month of year, hour of day, minute of hour, week of the year, and year are transformed using one-hot encoding. So we have timestamp component, processed input result, and transformation. So Unix time in seconds, day of month, day of week, month of year, hour of day, minute of hour, and week of year. So this is something that you should be just aware at a very high level, that these timestamp components are available, like these functions or component, and you can actually make model or predictions. You can consider take into consideration when you create your model. Okay, category feature encoding methods in generalized linear models. So in generalized linear models, GLM, feature encoding can be specified using the model option, which is category encoding method. It supports two methods for category feature encoding. One is one-hot encoding and dummy encoding. I'll be covering both one-hot encoding and dummy encoding next slides. And you have to do all these two. So one-hot encoding maps each category of a feature to its own binary feature, where 0 represents the absence of the feature and 1 represents the presence of the feature. So 0 is absence, 1 is presence. This method creates new feature columns equal to the number of unique categories for the feature across the training example. So for example, for a feature column name, so I'll just showcase this, it would be much easier. And we'll just see one-hot encoding. Okay, so this is how it looks like. So one-hot encoding maps each category of a feature to its own binary feature, where 0, as I mentioned, is absence and 1 is the presence of feature. So this method creates new feature columns equal to the number of unique categories for the feature across the training table. So for example, for a feature column named fruit, so in your data set, apple, banana and cranberry, so let's say there are 10 records, but 3 are these unique categories, so apple, banana and cranberry. There could be millions of records, like millions of rows, but if these 3 are the unique categories of fruit, then it creates a binary column for each category. So this will be transformed into something like this. So this is the original data, and once it's transformed, there instead of fruit column, there will be like fruit apple, fruit banana and fruit cranberry, and you will have so for the first row, there are other columns also in this data set, but we'll just ignore it for the sake of this example. So we have 1 for row 1, and fruit banana is 0 0. So these two columns will be 0, and this is yes, and others are no. So second row same, 0 1 0. So no, yes, no, and third data row, no, yes. So this is one-hot encoding. Next is dummy encoding. So dummy encoding is similar to one-hot encoding, but creates n-1 placeholder. So it's just one data placeholder variables. There's 1 minus to represent n categories for a feature. The category with the most occurrences is dropped. Okay, so this will save some space or memory. And for example, for a feature column named fruit with categories apple, banana and cranberries, it creates a binary column for each category, excluding the one with the most occurrences. So it looks something like this. In the final set of, so in this case, we have, so third one, because there are 3 total unique values, so it will be 3 minus 1, so it will be 2. So you have fruit apple, fruit banana, so 1 yes, 0 0 1, and 1 cranberry we don't need because we can just specify 0 0. So if it is 0 0, it automatically indicates the third category. So third category this is like dummy encoding, and this is for the most occurrences. So in this example, you just imagine the cranberry is appearing most of the time. So for whichever is appearing the most times, that automatically gets 0 0. Okay. In the final set of weights from ML weights, the dropped category is included. Okay. In the final set of weights from ML.weights, the dropped category is included, but its weight is always 0 0, something like this. And in ML.advanced weights, the standard error and p-value for the drop value are not a number. And if warm start, so this is some extra information. If warm start is used on a model, then that was initially trained with dummy encoding, the same placeholder variable is dropped from the first training run. Okay. Understanding manual feature pre-processing. The transform clause of the create model statement allows custom data pre-processing, enhancing flexibility and control over the modeling process. And manual pre-processing functions are utilities that can be utilized independently or in combination with the transform clause to define tailored data pre-processing. Okay, understanding pre-processing functions. So we have type of function, definition, example, usage. So first type of pre-processing function is scalar. It operates on a single row. So this is, we are talking about transformation. And example is ml.bucketize, and usage utilized for individual data points. So there is ml.bucketize. For one more example will be ml.quantile bucketize. Second is second type of transformation function is analytic, and it operates on all rows, outputting the result for each row based on statistics collected across all rows. And example is ml quantile bucket. Sorry, this is in the analytic. So I made a mistake. And for this example is ml.bucketize, and this is ml.quantile bucketize. And usage, some usage instructions are: you must always use an empty. This is a over function. You must always use an empty over clause with the ML analytic functions. And when you use ML analytic functions inside the transform clause during training, the same statistics are automatically applied to the input in prediction. Okay, types of pre-processing functions. We have general purpose function pre-processing functions, like I'll just cover that, ml.imputer, which I'll be covering, and it can be used on string or numerical expressions to perform data cleanup. And we have categorical pre-processing functions. I'll be covering this. And third one is numerical pre-processing functions. So first is use the following function on string. So general functions on string or numerical expressions to do any kind of data cleanup. For example, there is one ml.imputer. This is for string or numerical expressions. Next we have this just to be aware of. I will not be going too much detail. So we have categorical functions. So categories, for example, the example which I have taken for the fruit, apple, banana and cranberries. So use the following functions on string expressions to categorize data. So you can have ml, the feature cross, hash bucketize, label encoder, multi-hot encoder, n-grams and one hot encoder. Third one is numerical functions, and use these following functions on numerical expressions to regularize data. So this is for numbers. So if the data column is numbers, you can use this bucketize, max, ab scalar, min max scalar, normalizer, polynomial expand, quantile bucketize, robust scalar and standard scalar. Okay, some limitations. BigQuery ML supports automatic pre-processing in the model export, but has a known limitation that it does not include manual pre-processing. So this is just to be aware of that. It supports automatic pre-processing in the model export, but does not include manual pre-processing. So when you do manual pre-processing, it will not automatically take care of any pre-processing. So you have to do manually. And that's all. Thanks for watching.